Okay, we're gonna continue on here, chapter 9, I think. Sounds like a good one, maybe. So we started talking about solutions in this chapter, and remember that solution is really made up of two parts. There's the solute, which is the smaller part of the solution, and there is the solvent, which is the larger part of the solution. And typically speaking, you dissolve the solute in the solvent. So, for example, if we had water and some sodium chloride solid, this guy would be our solute. This would be our solvent. The sodium chloride would dissolve in the water, and that would make basically an aqueous solution. And that's usually what the aqueous sort of means of sodium chloride. Now, we talked also about solubility. Remember, if something is soluble, then it really will mix together. If it's insoluble, it will not mix. And typically speaking, you'll get like a solid or a precipitate to sort of form. There's an idea of why certain things are sort of soluble in each other. And that was the idea that we talked about of like dissolves like. And things that use similar types of interactions with other molecules, the similar way that they interact with themselves or other of the same type of molecules, they will definitely be soluble in each other. If you put together two things where really they use very different, what is referred to as intermolecular forces, then they're going to have some trouble interacting with each other, and it's really those intermolecular forces that are important. And that's because things that are polar can do one of two types of intermolecular forces. They could do dipole-dipole interaction, or they could do hydrogen bonding, which is basically the same thing. And basically what that is the positive side of one molecule will be attracted basically to the negative side of another. And if something is polar, what that means again is that it has a fixed side to the molecule that is always going to be negative no matter what the situation is, and a side that's going to be positive no matter what the situation is. And that's like water, which is a polar molecule. It has a negative side and a positive side. Now, when we have nonpolar guys, they use, typically speaking, dispersion forces. And dispersion forces are relatively weak intermolecular forces. And they are weak because if it is a nonpolar molecule, it essentially will not have a charge, which makes it very hard to interact with other molecules because pretty much how all molecules interact with each other is like positive negative attraction. So these guys that are nonpolar, which really don't have any type of charge because their electrons are shared equally, has to rely upon something happening. Like, for example, as we might have talked about a little briefly there, electrons in one of them may be going to one side of the molecule versus the other, and that will temporarily create a charge in that normally nonpolar molecule. If that guy is still next to this guy, that will cause the electrons in that guy to really head to the one side versus the other and create a temporary charge in that molecule. And now they have a way again to interact. But as soon as the electrons kind of go back to where they were, they will break apart and kind of make new interactions and break apart and make new interactions. They do not have a system sort of set up to maintain a long-term positive negative attraction with somebody that's polar. That's pretty much how they want to do it. It's just maintain that interaction. So that's why when we think about like dissolves likes, things that are ionic and polar, they are all good. They're going to mix really well with each other. Things that are polar and polar will also mix well with one another, again, because they're going to use the same type of forces. And also the one that sometimes people miss is actually nonpolar guys and nonpolar guys will also interact well with each other. And again, it's for the same reason. They're just using the same type of force that they use with themselves as to what they would use with somebody else. You really only have sort of a problem when you try to cross over polar and nonpolar. They're going to be really insoluble in each other because, again, they're going to use very, very different ways to try to interact with one another, and they're not going to be able to maintain that. So we talked about that there. We talked about electrolytes as well. Remember, electrolytes are things that will break apart into ions in solution. And because there are ions present, it can conduct electricity. And there is a strong electrolyte, which basically will 100% break apart. So if you had something like, for example, a sodium chloride solution, in the actual solution, you would have sodium ions and chloride ions. And that's pretty much it. You would have 100% in that beaker, just the ions floating around. There would be no sodium and chloride units still together. They will all completely just fall apart into ions. That's why it's a really good conductor of electricity, because essentially in your beaker you have nothing but ions floating around, which is pretty much necessary for electricity to be conducted. There's also weak electrolytes, and weak electrolytes will mainly stay together, but will break apart a little bit into ions. And because it's still able to break apart a little bit into ions, it is still able to conduct electricity. Again, nowhere near what a strong electrolyte could do. So we saw like the light bulb example, for example, a strong electrolyte light bulb would go off very, very brightly. A weak electrolyte, the light bulb will go off really dim, but it will still go off. It's still able to conduct some electricity, but it will not be as bright or as strong as a strong electrolyte. Something like hydrofluoric acid, which is a weak acid, and most weak electrolytes or weak acids or weak bases will break apart a little bit into H plus and F minus. And in this case, this is actually mainly what you have in solution, and you have a little of these guys. So if you were to look at a beaker of that, you would mainly see the HF unit still together, but you will see a little bit of some ions also floating around in the solution. And again, that presence of those little ions will allow it to conduct electricity. It is nowhere near what you would see in this case, where you got pretty much 100% ions floating around, and that's going to make it a much stronger conductor of electricity. The other sort of difference in terms of the equation is the arrows. In a strong electrolyte, it's a one-way arrow. Everybody's dumping out to the product side. Nobody's coming back the other way. In a weak electrolyte, we have a reversible reaction, where at some point, some of those products will actually recombine and come back the other way towards the reactant. So it's like a two-way street sort of happening, a forward direction and a reverse direction in a reversible reaction. Then we have non-electrolytes, which do not break apart into ions. And because there pretty much is no ions, it will not conduct electricity, but it can still dissolve, like sugar, for example. Sugar will dissolve in something like water, and it's able to do so, as we saw earlier, that has a bunch of OH groups on it and makes it pretty soluble. The difference is something like sugars, carbon, hydrogens, and oxygens. That is all nonmetals. That's all sharing of electrons, no ions being formed in this case. So although it will dissolve, it will not produce the ions necessary to conduct electricity. Lastly, we talked about these guys. We talked about equivalents. And equivalents are essentially a conversion factor that we use a lot of times with electrolyte solutions. It is based on the charge of the ion that's present. And it doesn't matter really if it's a positive ion or if it is a negative ion. It is actually just the number here that's important. So we could come up with a conversion factor that 1 mole of sulfate gives you 2 equivalents. And the 2 is basically from the charge. And the same thing here, if we had 1 mole of calcium, that would also be 2 equivalents in this case because of the charge. So a lot of times we may convert from molarity like we did last time there, moles per liter, into something like equivalents per liter or milliequivalents per liter, which is commonly used sometimes for electrolytes. And as we saw, for example, I think we might have looked, I don't remember which one we looked at, but if we looked at something where there's sodium ions and maybe there's sulfate ions, and when you calculate the equivalents per liter for the sodium and the sulfate, and also the milliequivalents per liter of the sulfate and the sodium, what you'll see is in those couple examples that we did, for each the positive ion and the negative ion, they will end up the same concentration of equivalents per liter because it's based off the charge. And when we put an ionic compound together, we make sure the overall charge is 0. And that means in terms of the charge sort of concentration, we actually have the same sort of charge concentration in that solution, and they should always be that way. If you have a cation and anion in an electrolyte solution and you calculate either of these guys here for both of them, they should end up being the same for both, because it should be a balanced ionic compound of positive and negative charges in there. Any questions on any of that stuff there we talked about last time? Okay, then we're going to continue on, and we're going to talk about now concentration units for solutions. So the first type of concentration unit we're going to talk about is mass percent. It is sometimes abbreviated percent mass to mass, and sometimes referred to as mass to mass percent. To calculate the mass percent of a solution, you would take the mass of the solute divided by the mass of the solution, and you would times it by 100%. The important part of this type of calculation is actually the bottom. And remember that the bottom is made up of 2 things. A solution is a solute plus the solvent. So you definitely want to make sure when you're doing that calculation that you do get both of those numbers. The reason why it's important to do so, especially with mass percent, is I would say it's super common in those type of problems that they will break those numbers up and give you the mass of the solute separate from the mass of the solvent. And it's a very common mistake that people make, which is they just end up dividing by the mass of the solvent rather than the entire solution together. So you definitely want to make sure that you have the mass of the entire solution. Now, for example, if I had a mass percent given to me, like if I had one that said 4.5% by mass sodium chloride solution, I can turn that percentage into a usable conversion factor, which sometimes is easier to do than plug and chug into the equation. And the way I would do that is like normal percentage rules, which is if you have a percentage and you want to kind of turn it into a usable type of number, we usually assume that we have 100 of something, right? And what that does is it keeps the percentage the same number, so you don't have to change numbers or anything like that. So if we take that assumption, we could actually turn this into a usable conversion factor. And what that would mean is that we have 4.5 grams of sodium chloride in 100 grams of solution. So that is a basic kind of conversion factor that we could get from that value or that concentration that we could use. And because it is a conversion factor, we could also flip it around the other way and put the 100 grams of solution up on top and the 4.50 grams of sodium chloride on the bottom. So sometimes when you're doing problems and you are given the mass percent, sometimes it's just as easier to do it more like a dimensional analysis conversion problem and turn that percentage into a conversion factor and just kind of use it like that. Any question on that there? All right, why don't you try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent? of calcium chloride in the solution. So let's see what you come up with here. Okay, so let's take a look here. Obviously, here we're looking for percent mass to mass. So that is our formula we saw, which is the mass of the solute divided by the mass of the solution times 100%. In this case, we have 2.5 grams of calcium chloride. That is the smaller part of the solution. That is the solute. Water here is the solvent, as it works good for a ionic compound. So we have our mass of solute, which is 2.5 grams. We have our mass of our solution that we need to calculate. Remember that the mass of the solution is the solute plus the solvent. So here we would want to take 2.5 grams and add it to 50 grams. And that is going to give us the mass of the solution and not just the solvent. And we'll have 52.5 grams of solution. Again, that is what needs to go on the bottom, not just the solvent. And if we put that in there, that'll give us 2.5 grams divided by 52.5 grams times 100%. That is 2.5 divided by 52.5 times it by 100%. Going to give us 4.76%. You could label this M/M, which stands for mass to mass percent. You want to get really fancy with it, calcium chloride, which is what we're talking about in this particular case. Any questions on that calculation? Again, getting the mass of the solution is really important. It's very, very common. These have problems that they do separate out those values. And again, very common that people just divide by the solvent rather than adding together and getting the solution. Any questions on that there? All right, then let's try another one. Concentrated hydrochloric acid solution contains 37.2% by mass. What is the mass of hydrochloric acid contained in 35.5 grams of the solution? So let's see what you end up with here. Bless you. Bless you. Okay, so let's take a look at this one here. We have the mass percent given to us, which is 37.2%. We're looking for the mass of the solute here, which is our HCl. And that is what we're looking for. By the way, I know that is the solute, and that's what I'm looking for because we're looking for the mass of the HCl. Remember that the name of the solution is the solute. So if you're looking for HCl, then you're looking for the solute in this case. That means that the other number, like it says there, is our solution, which is 35.5 grams. Now, clearly, you can plug and chug into this equation here if you like and solve for what you are missing, which in this case would be the top there. That would be what you're missing. You have pretty much that, and obviously you have that. The other approach you could take is you could take more dimensional analysis approach. So since it is 37.2% by mass HCl, what that means is there are 37.2 grams of HCl in 100 grams of solution. Or you could flip it around, 100 grams of solution is 37.2 grams of HCl. So if you don't want to remember the formula, you could just take a more dimensional analysis sort of approach to it, which is, I know I have 35.5 grams of solution. Remember that opposites cancel, which means I do need solution on the bottom, which would be that guy right there. 37.2 grams of HCl divided by 100 grams of solution. The grams of solution will cancel, And we'll have 35.5 times 37.2 divided by 100. It'll give us 13.2 grams of HCl. By the way, that is the exact same math you would do if you just plugged it into the equation as well, but can't remember the equation. Again, you could turn that conversion factor or turn that percentage into a conversion factor and just kind of take it like getting rid of the units you don't want to keep the units that you do want. Any questions on that? And again, you basically, if you plugged it into the equation, you would go 37.2% equals my grams of HCl divided by my 35.5 grams times 100%. You would divide the 100 to the other side, which is what it is right there, and you would multiply the 35.5 to the other side, which is what it is right there. So again, it's same math. You plug it in or do more of a conversion factor way. Any questions on that there? Now there are similar percent concentrations to mass percent. The next sort of percentage concentration is volume percent or volume to volume percent. The percent volume to volume is the volume of solute divided by the volume of solution times 100%. This is kind of like milliliters over milliliters. The other one's kind of like grams over grams, mass to mass. So this is volume to volume. This is the percentage they use for like alcohol, percent volume by alcohol and stuff like that is this sort of concentration. Works the same way as the other one. If you had a 4.5% volume to volume sodium chloride solution, you could also turn that into a usable conversion factor. That would mean you have 4.5 milliliters of sodium chloride in 100 milliliters of solution. Or again, you can flip it around the other way. 100 milliliters of solution, you would have 4.50 milliliters of sodium chloride. So again, just like the other one, you can kind of turn the percentage into a usable unit. The good news on this one is, unlike probably mass percent, in these type of problems, they typically will probably just give you the volume of the solution without you having to like add the parts together. So very commonly on this one, you don't have to necessarily do the adding of the parts of the solute and the solvent like you do on the mass percent. So this kind of, again, milliliters over milliliters is usually what we look at. The third sort of percentage is mass to volume percent, and that is percent M/V, which stands for mass/volume. And that is the mass of a solute divided by the volume of solution times 100%. That is grams per mass and milliliters for volume. It's kind of like density, grams per milliliter in a sense. And same idea with this one. You have that 4.5% mass to volume sodium chloride solution. That would mean you have 4.5 grams of sodium chloride in 100 milliliters of solution. Or again, you can flip it on its head there. 100 milliliters of solution would contain 4.5 grams of sodium chloride. So also like the volume one, this one typically as well, you'll be given probably the volume of the solution without having to worry about adding. So probably the adding of the solute and solvent most likely is going to occur with the mass percent calculation. These two, usually you'll have the volume of the solution sort of given to you. Any questions on any of those there? All right, so why don't you try this one here? What is the mass to volume percent of Br2 in a solution prepared by dissolving 12 grams of Br2 and enough carbon tetrachloride to make 250 milliliters of solution? Okay, so let's take a look. We're looking for the mass to volume percent here. That's M/V. That again is the mass of our solute divided by the volume of solution times 100%. In this case, it is the Br2 here that is our solute. In this case, it's actually the carbon tetrachloride is our solvent in this particular case. And the reason that is Br2 is polar or nonpolar. It is nonpolar as they're identical, right? And they share the same electronegativity value. And that's a nonpolar molecule, which means if you try to use water here, that's a really bad choice because water is going to want to use hydrogen bonding. This guy's going to want to use dispersion forces. They're not going to mix. But if you quickly sketch out carbon tetrachloride, it kind of looks like this without all the electrons drawn. That is one of those symmetrical geometries, no dots on the central atom. Everybody on the outside is the same. That is also nonpolar. So these two guys work really well together because they're both nonpolar. They both use the same type of interaction in this case. And again, if you tried to use water here, they would just separate out from each other. They really wouldn't interact. So in this particular case, we do have the mass of the solute, which is our 12 grams. We do actually have the volume of solution that was given to us, which is 250 milliliters. So really all we have to do is plug that in. So 12 grams divided by 250 milliliters times 100%. We will end up with here 4.8% M/V Br2 in this case. Any questions on that? So typically in terms of your answer, you could give it as a percentage since that is what you're really calculating, which is in this case, the mass to volume percent. Obviously the units there don't really cancel out, but you can leave the answer as percent mass M/V. Any questions on those three percentage type calculations? All right, one more here. Calculate the grams of KCl and the grams of water in a 225 grams of an 8% mass to mass KCl solution. So we're looking for the mass of the solute and the mass of the water, which is our solvent in this case, in this solution. Okay, so let's take a look. Obviously, we're dealing with mass percent. So we'll look at the equation here. Mass percent. Mass of our solute divided by mass of the solution times 100%. Again, here KCl would be our solute and water would be our solvent in this case. We do have the mass of the solution given to us, which is 225 grams. We also have the percent mass to mass given to us of 8%. Again, we could convert that into a conversion factor, or we could just plug it into here. We definitely have this number and we have this number, which means we can solve for the mass of the solute, and that will essentially give us the grams of KCl in this solution. And if I do that, I would have 8% is equal to the mass of our solute divided by 225 grams times 100%. Once again, here we will multiply the 225 to the other side and then divide the 100. If you did not want to do it that way, again, you could turn this into 8 grams of KCl and 100 grams of solution. Or in 100 grams of solution, there are 8 grams of KCl. And you basically could do 225 grams of solution. Use the conversion factor on the left there, 100 grams of solution is 8 grams of KCl. That will give you your multiplying by 225 and your dividing by 100, without having to rearrange the equation. So whichever way you like to do it, you get you the same answer. If you do either way, that should get you about 18 grams of KCl. And that basically is what you would have on the other side. If you did this guy, it would be the mass of the solute would equal 8% divided by 100% times 225 grams, basically, if you rearranged it. Any question on that one there? That is only half the answer, right? That is the grams of KCl are our solute. We know that the mass of the solution is equal to the mass of the solute plus the mass of the solvent, which is the water in this case. So we now know the mass of the solution is 225 grams. We just figured out that I have 18 grams of my solute plus the mass of my solvent. That means I'm going to subtract 18 grams to both sides. And that will give me that the mass of my solvent, or water in this case, should be about 207 grams. Any questions on that one there? So again, it is just up to you with these if you want to plug it into the equation and rearrange it, or use it more as a conversion factor if you're given the percentage. Again, sometimes it's easier so you don't have to rearrange things to kind of do it that way. Any questions on that there? Yeah. Water is the solvent in this case. Again, because really KCl is an ionic compound, so probably 9 times out of 10, if not 100, water probably would be your solvent if you have some type of ionic compound. Other questions? Again, in the last example we did with the carbon tetrachloride was the solvent because our solute was the Br2, which was nonpolar. So water would not be a good solvent for that one. Other questions? All right. So then let's talk officially about molarity, which is, I would say, probably the most common unit of concentration that you see. Again, you probably have seen it on your bottles in lab. Usually a big M is the abbreviation for molarity. So molarity is moles per liter is the units of it. So big M, the real units are moles of solute divided by liters of solution, but most people just call molarity big M is moles per liter. So that is definitely the most common unit of concentration that you come across. If you have something that is, say, 4.5 molar, and that's how you refer to it, sodium chloride, and you're going to use it in a calculation, as I might have mentioned last time, I would 100% of the time get rid of the big M and use it like a conversion factor. And what that means is that is 4.5 moles per liter of sodium chloride. The number always stays with the moles part, and it's always per 1 liter. You could use that as a conversion factor if you needed to, and you could flip it around the other way and put the moles on the bottom and the liters on top. But this way is probably the proper way to do it than leaving it with the big M in your calculations, because as I mentioned before, I would say most commonly done when people see the big M, all they think about is moles. They have no idea about the volume, no idea about the liters. So if you get rid of the big M and put both of those units, you hopefully will not forget about them because they are staring at you on the paper. You can see the liters. You can actually see where the liters are. Is the liters on the bottom? Is the liters on the top? And you can take a more dimensional analysis type of approach to calculating this. We oftentimes will solve for any one of these 3 things. So if you want liters, that is moles divided by molarity. And if you want moles, that is liters times molarity. I would say that these 2 right here, all 3 of them really, But these two right here are very, very common ways that we use molarity, and we use molarity and volume together to get the moles. That is a very common sort of calculation in chemistry. 100% of the time, if you are using molarity and you're using a volume, it needs to be in liters. Yes. Because if you leave your volume in milliliters and use it with molarity, you will not get moles. And you might think you're getting moles, but you are not. So you do have to convert it to liters, because if you take milliliters times molarity, you do not get moles. You get what are known as millimoles, which is about 1,000-fold off of what you think you're getting. Yes. So if you don't want to do that, and most of the time you need moles and not millimoles. So most of the time you need those moles. So make sure it's always in liters when you're using volume with molarity. Again, a very common conversion is 1,000 milliliters is equal to 1 liter. So that again is something that we use a lot with concentration and solutions. Any questions on that there? All right, I can. So as I mentioned before, you can do molarity as millimoles over milliliters, and the reason it works is the millis cancel out, and you're left with moles per liter, basically. But definitely molarity by itself, make sure it's in liters, because pretty much 99% of the time you need moles and not millimoles. And if you don't recognize that, you will be off by a factor of 1,000. So I would always recommend liters with molarity for sure. Good. Yeah. Okay. So again, if we do have a solution that has a concentration of molarity, um, it is basically 1 molar sodium chloride. That means that we have 1 mole of sodium chloride dissolved in enough solution to make 1 liter solution. And how concentration works with molarity is sometimes we may be interested in just the individual ions and not necessarily the entire ionic compound together. And to show you again how that sort of works, we sort of touched upon it when we were talking about equivalence. So if you have 1 molar sodium chloride, what that means is basically sodium chloride will break apart into sodium ions and chloride ions. And the way that we could relate the concentration of the entire ionic compound to each of the ions is very similar to what we do with stoichiometry, which is kind of like a mole to mole relationship. So for every one of these sodium chlorides, I have 1 sodium ion. So basically, the concentration of the sodium ions in that solution would be 1 times 1 molar, which means it would be 1 molar sodium ions floating around in that solution. Now, if I was interested in the chloride ions by themselves, we could do the same thing. It is a 1-to-1 relationship between the whole thing and the chloride ions. And that would mean we would also multiply the concentration by 1, and that will give us 1 molar chloride. Concentration is not additive, because clearly if you add 1 and 1, you get 2. But in this case, you add 1 and 1, you get 1 in terms of the concentration. It is the proportion of these ions that are floating around in the solution. You basically, when you drop sodium chloride into a solution and it breaks apart, because it's a strong electrolyte, you basically get a 1-to-1 relationship between how many sodium ions you get and chloride ions you get. That is different than if I had a 1 molar solution of iron 3 chloride. And if I had a 1 molar solution of iron 3 chloride, when this would break apart, this iron 3 chloride in solution, I will get 1 iron ion floating around, and I will actually get 3 chloride ions that are floating around in the solution. So when we look at the concentration of the whole thing, which is 1 molar, the relationship between the whole thing and the iron is also a 1-to-1 relationship, just like you do stoichiometry, kind of the coefficient. You would take 1 times the 1 molar, and that will give you 1 molar iron 3 guys floating around. But when I look at the chloride, it is a 1-to-3 relationship, which means I need to take the concentration of the whole thing and multiply it by 3 to give me the concentration of my chloride ions, which in this case would be 3 molar. Because every time that unit of iron 3 chloride goes in for a swim, you get 1 iron atom to 3 chloride atoms, 3 times as concentrated in chloride per iron, right? Because you get 3 per 1 on that deal, right? 3 of those going in to only 1, so 3 times as concentrated. That is the quick way that you can calculate the concentration of ions from the actual whole thing. The long calculation to show you how we get there is this. If I took my 1 molar iron 3 chloride and I break it apart into my moles per liter, I could do my mole to mole relationship just like in stoichiometry. It's a 1 mole of the whole thing to 1 mole of iron. And I do 1 mole of the whole thing here to 1 mole of the iron 3. Moles of the whole thing cancel, leaves me 1 mole per liter of just the iron 3, which is the exact same thing as I have here. Now I could do the same thing for the other ion, which is 1 mole of the whole thing per liter. And for the other guy, 1 mole of the whole thing gives me 3 moles of chloride. So 1 mole of the whole thing gives me 3 moles of the chloride ions. Moles of the whole thing cancel. Gives me my 3 moles per liter of chloride. That is why I multiply it by 1. That is why I multiply it by 3, basically. So that is why we do the quick way, if you want, without having to do the calculation. You basically can multiply the whole concentration by whatever the ions break apart into. If it breaks apart into 2 ions on the other side, multiply the concentration by 2. Breaks apart into 3 like I did there, multiply it by 3, 4, 5, however many ions you have going on there. Question on how to relate the concentration of the ionic compound to its ions. So again, whatever it breaks apart into. So for example, if I had calcium hydroxide and I had a 2 molar solution of calcium hydroxide, what would be the concentration of the calcium ions and the hydroxide ions in that solution? Take a moment and calculate those, guys. So what is the molarity? Is how this guy is going to break apart. So this guy, when he breaks apart, will give us 1 calcium ion. And again, the 2 means that we will get 2 hydroxide ions floating around in that solution. So again, if you do the quick way, you're just going to kind of think about how many of those guys you get. So it is a 1-to-1 relationship between those two. So if we're looking for just the calcium ion concentration, we would take 1 times 2 molar, which means we would have 2 molar of the calcium ions, as it's a 1-to-1 relationship. Now, if we look at the hydroxide, it is not a 1-to-1 relationship. It's a 1-to-2 relationship. We get twice as much hydroxide floating around as we do calcium. So how that affects concentration and molarity is we need to multiply it by 2. And that would give us 4 molar of hydroxide ions floating around in that solution. Question on that there. So like I said, sometimes with concentrations and stuff, you may be asked about the individual ions rather than the entire ionic compound together. And that's really the quick way that you can sort of figure out the concentration of the ions is basically just figure out how many of each of those ions it breaks apart into. And then all you have to do is multiply that number by the concentration of the whole thing. And that will basically get you your concentration of the ion that you're looking for. Any questions on that there? All right, so let's try a real molarity question here. What is the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters of solution? Some information might be helpful for you. Potassium is 3910 and Br is 7990 from the periodic table. So we're looking for the molarity, the moles per liter here of our KBr solution we made. Let's see what you come up with. Okay, so let's take a look, see how you're doing. So obviously here we are looking for the molarity, which is moles per liter. And in this case, we have 15.6 grams of KBr and enough water to make a 1.25 liter solution. So that is the volume of the solution. So that is actually the bottom part that we need, right off the bat. In this case, it's actually in the right units, it's in liters. Again, very commonly, though, a lot of times volume's given to you in milliliters. So you do have to a lot of times do the 1,000 milliliters to liter conversion. But in this case, it actually is in liters. We're good. This is not in the units we need, which is moles. It's in grams. So we do need to convert that into moles before we could use it. And that is where the molar mass comes from, like we did before. Remember, grams to moles, which is a very common conversion that you do with these problems. The molar mass from the periodic table is going to allow us to do that. In this case, we actually just need to add these together, I think. We got one of each. So that will give us 119 grams per mole is the molar mass of KBr. We're going to use that again as a conversion factor to put our grams into the correct units. So we do want grams on the bottom so they cancel. So 119 grams per mole of KBr. The grams will cancel, and that will get us here 15.6 divided by 119. We'll call it 0.131 moles. That is basically now the top part that we need to calculate our molarity. So now we always do is put it in there. So 0.131 moles divided by our 1.25 liters. And it's going to get us something like 0.105. Now the units on this does not cancel out, so you can leave it one of two ways. You could leave it as moles per liter, and again, the moles stay with the number, and you could call it KBr. Or if you want at this point for your answer, you can put the big M back in and do KBr as well. So either way is acceptable in terms of units here at the end. Any questions on that calculation there? So again, those are, like I said, very common conversions you have to do in addition to using molarity, grams to moles or moles to grams, and also milliliters to liters or liters back to milliliters. So those guys are used a lot with molarity and concentrations. All right, let's take a look maybe at another one here. What is the mass in grams of sodium nitrate that's required to make a 2.5 liter solution that has a molarity of 0.15 molar? Let's see what you come up with. Sodium from the periodic table, 2299. Nitrogen, 1401. And our friend oxygen, 16. All right, so let's see. Obviously, here we're going to be dealing with molarity as is given to us. So definitely moles per liter. So here we definitely have a volume that is 2.5 liters. We do have a molarity given to us of 0.15 molar. And here we're looking for basically how many grams. So if you're not really sure where you should go or maybe how to begin, you could just think about molarity. Obviously, you need to use it And obviously here we do have molarity and we do have volume given to us. So really the only thing we don't have is moles. So that's probably a pretty good place to start. And that does make sense because we eventually want to get to grams. So we do know how to go from moles to grams. That again is going to be our molar mass from the periodic table, right? That's going to allow us to do that. So we want to think about how we want to do this. We want to make sure we are in liters, which we are for the volume. Once again, if it's not in liters, you should probably convert it. I again am going to convert this into really a more usable conversion factor. And again, it allows you maybe not to have to rearrange the equation or something like that. So when it says 0.15 molar, what that means is I have 0.15 moles per liter of sodium nitrate. Or I could flip that around, put the liters on top, and 0.15 moles of sodium nitrate on the bottom. Now, by doing that, I don't even have to really play around with rearranging this equation. I again could just take a dimensional analysis approach and get rid of the units I don't want. I could take my 2.5 liters, and now all I have to remember is opposites cancel. So I would want to use this guy over here on the left to do so. And that would give me moles per liter of my sodium nitrate. The liters will cancel, and that will give me the moles that I got going on here, which is 2.5 times 0.15, and gives me 0.375 moles of sodium nitrate. So again, by doing that, I really didn't even have to touch this equation or rearrange it. All I had to just get rid of the units I don't want. By the way, obviously, when you rearrange it, it is the same calculation we just did, but you don't have the stress of did I rearrange it correctly, because all I have to do is the opposite, and it will do the math for you without having to rearrange it. At this point, I'm close to what I need, which is how many moles, but I actually do want grams. So as I mentioned before, we will need the molar mass from the periodic table to do that. So in this case, we have one sodium at 2299. We have one nitrogen at 1401 from the periodic table. And we have three oxygens, each at 16. From the periodic table there. That's going to give me a molar mass of 85 grams per mole when I add all that together. That again is going to be used as a conversion factor, so I don't have to do any rearranging. I just want to go opposites to cancel, which means I need moles on the bottom and my 85 grams there up on top from the periodic table. And that's going to get me here about 31.9 grams of sodium nitrate. Question on that calculation. Now, what does that number mean? That number means that if you wanted to make this solution, you want to make a 2.5 liter solution that had a concentration of 0.15 molar, you would have to weigh out 31.9 grams of sodium nitrate, dissolve it in some water, enough water until you get a final volume of 2.5 liters, mix it up really good, and you would now have a solution that has that molarity, basically. So that is what that number represents. Any questions on that calculation there? So again, hopefully you're seeing that you take a dimensional analysis approach to a lot of calculations. It will allow you not to have to worry about rearranging equations, because if you just go opposites to cancel what you don't need, it will again do the math for you, basically. Yeah. All right, let's take a look at this here. So for each of these solutions here, what is the concentrations of the ions that are present in each of these? This one and this one, two separate ones. So for the first one, we're looking for the concentration and molarity of the sodium ion and the sulfate ion. What is the concentration of each of those, molarity? And for the second one, what is the concentration of potassium and chromate? Okay, so let's take a look. So remember on these, if we're looking for just the ions from an ionic compound, the first thing we want to really think about is how it breaks apart. And in this particular case, because there's a 2 here, that means I will get 2 sodium ions and I will get just 1 sulfate ion basically here. And that's really all you need to figure out the molarity of the ions. And we're just going to go with the 1.2 molar for the whole thing. It is a 1 to 2 relationship here, as we talked about. So to get the concentration of the sodium ions, we're going to take 2 times the 1.2, give us 2.4 molar for our sodium ions. Now, for our sulfate, it is a 1 to 1 relationship, which means concentration really doesn't change. We take 1 times our 1.2 molar, and we end up with 1.2 molar for our sulfate in this case. So the sulfate ions floating around that solution has a concentration of 1.2 molar. The sodium ions floating around is 2.4 molar. Again, you get 2 sodiums for every sulfate. It's a 2 for 1 special. So you got twice as much sodium as you do sulfate floating around. So the concentration of sodium is twice what it is of sulfate. Any questions on that one there? Looking at the bottom one, same idea. We want to think about how potassium chromate will break apart. And it will break apart into 2 potassium ions. And I know that because there's a 2 there, and that's what that basically means. That is because potassium is K plus and chromate is -2, and that means you need 2 of those guys to balance it out. So we will get 1 chromate here. And again, for 0.75 molar for the whole thing, a 1 to 2 relationship means we would take 2 times our 0.75 molar, would give us 1.5 molar for potassium in this case. And it is a 1 to 1 relationship here, which means we take 1 times our 0.75 molar, gives us 0.75 molar of our chromate in this case. Once again, same idea here. For every one of those units that go for a swim, we get twice as much potassium ions floating around as we do chromate. So the concentration of potassium ions is twice that of